This paper tackles a practical failure mode of zero-shot image recognition in agriculture. Vision language models like ClipCan, in principle, classify images using only text labels. So instead of collecting thousands of annotated leaf images for every new disease, you could type apple scab and let the model decide. But for plant pathology, this promise mostly collapses. Leaf disease imagery and subtle symptom patterns are underrepresented in the huge internet-scale corpora VLMs were trained on, and short class names don't capture the fine-grained color and texture cues that actually distinguish diseases. As a result, vanilla clip lands in single-digit accuracy on the PlantVillage benchmark. The goal of the paper is very specific. Push zero-shot plant disease recognition as far as possible using only inference time. Prompt engineering, no gradient-based fine-tuning, no training images, no synthetic data generation, and no extra supervision. The proposed recipe, Crop Zero, is built around constructing a rich prompt universe for each class so that the text side of the model better matches how symptoms look in regions, and then scoring images against these prompts in a way that sharpens class boundaries. The headline claim is that, on PlantVillage, this purely inference-time approach raises top 1 accuracy from 8 to top 4% to 32, 0% a 3, a shale tree sifat. 8 jump, while staying lightweight enough to run quickly on a single GPO. The method itself is simple to describe, but carefully assembled for each disease class. They generate multiple families of prompts: generic photo templates, a close-up photo of a dew, multilingual variants in Spanish and French to tap into non-English text, image associations learned during pre-training, symptom-centered templates that explicitly mention lesions and infection patterns, and a large set of color by severity, snippets that combine hue adjectives, severity words, and disease nouns to mirror the visual reality of plant symptoms. They further expand prompts using Latin pathogen names when known, and handcrafted synonyms like rust, pustules, or powdery mildew, ending up with hundreds of unique prompts per class after removing duplicates. At inference time, they encode each image and compare it to all prompts for each class, using the maximum similarity over a class prompt set as that class's evidence, so the class can win if any of its prompts aligns well with the image. They also introduce a small negative bank of embeddings for unrelated everyday scenes, and subtract the strongest negative similarity from every class score, which acts like a contrastive sharpening step that discourages overly generic matches. Architecturally, they keep the VLM frozen and use 2 public clip checkpoints at 2 image resolutions, averaging their normalized embeddings. As a dual-scale ensemble, then apply temperature scaling per crop type, tuned on a tiny split and then frozen to calibrate logits. Evaluation is done on the official PlantVillage test set while discarding all training images with no augmentation. In results, their approach outperforms several recent zero-shot baselines, improving not just accuracy but also macro, precision recall, and F1. Remaining errors cluster around pairs that are genuinely visually similar, like potato early versus late blight, suggesting prompt expansion eventually hits diminishing returns. Ablations show the gains add up, removing multilingual prompts, symptom synonyms, or dual-scale ensembling. Each drops performance, confirming each component contributes. The conclusion is that sophisticated prompt engineering, plus a few inference-only scoring tricks, can close a large portion of the zero-shot gap for plant diseases using an off-the-shelf VLM. And the authors point toward next steps like dynamically selecting prompts conditioned on visual features and combining RGB with inexpensive additional sensing such as hyperspectral bands.